Okay, so we finished up on the last video talking about the generalized compressibility factor. We said that if we observe different gases based on what we call the reduced pressure and reduced temperature, they follow patterns. They all follow the same pattern. That's the whole point of this chart, is they're saying, look, for all of these different substances, notice they all kind of follow these same curves, and that tells us something. That tells us that while gas is not exactly ideal, we could maybe use how they all behave the same relative to a certain point. Well, that point they're relative to is the critical point, right? So the generalized compressibility factor says this. What its goal is to improve the ideal gas. Okay. Now, how it does that? Well, what it does is it says PV, little v, is equal to Z, the generalized compressibility factor, times R times T. And that's where Z is equal to the V if we took the specific volume of actual gas compared to the specific volume of that same gas if that gas actually behaved ideally. Okay. So what that's telling us here is, again, we can get a better prediction than the ideal gas law of what the actual substance would do. This Z value is going to be, as we saw on this chart here, is going to be a function of what we call the reduced pressure and the reduced temperature. Now, those reduced values, the reduced temperature is going to be the temperature divided by the critical temperature, and the reduced pressure is going to be the pressure divided by the critical pressure. Now, what are these critical pressures and temperatures? We'll remember our chart here. And P or T, V, U, H, or S. That's my critical point. Right there, the top of the dome. That's what these are. This is the temperature at that critical point, the pressure at the critical point. Take these ratios, find where they intersect, right? So, given a reduced pressure and a reduced temperature, you go find where the two intersect, come over and find a Z value, plug that in here, and the Z value now corrects the errors associated with the ideal gas law. We'll work an example problem. We should have a minute or two to do that at the end here. Okay, so don't worry if that seems a little foreign or Greek. I'm not going to ask you to use a generalized compressibility factor on a regular basis. I've already shown you the reduced values here. That's these equations up here. Okay. So it have place. As I mentioned before, I'm normally working. I've got a smart board where I can draw on these PowerPoint slides as we go along, so it's left myself room to draw on this. Okay. So again, I'm normally not going to ask you to find a Z value. You can if you want to, but if I'm dealing with air or an ideal gas, then an ideal gas law will be fine for most of our applications. Just understand it's only an estimate, but the Z value will improve it, will make it better. Okay, equations of state. So there are other equations of state. In our text, section 3.8 talks about other more robust equations of state. The ideal gas law is the simplest of equations of state that we can use. But as we've seen, there are errors associated with using it at certain times. The compressibility factor greatly improves the ideal gas law without too much effort. Then there are more, as I said, more robust, more powerful equations of state that are a little more mathematically complex to deal with, but they do produce better estimates. They minimize the error. They have much less error associated with them than the ideal gas law. You typically can find this graphic within your text. they've plotted the specific volume down here per mole and on a logarithmic scale. But this is still your saturated dome, and they're still showing you the error associated with using these different models here. And so I'm not going to go too far into that. The moral of the story here is if you need something, a better equation of state than just the ideal gas law, you're probably going to use a computer program to do this for you. But you need to be aware of what they are. Okay, I know, and if you go on to grad school, you probably will build, it's not uncommon, you'll build some kind of simulation utilizing one of these higher order equation of state models. Okay, so anyway, I think that's really all we would need to talk about here, is just understand there are things better than ideal gas law. They're a little more difficult to use. If you need to use one of them, you can go back to a thermotext, find the section talking about equations of state, and you can find at least basic information about more robust equations of state. Okay? How are we on time? Okay, we won't get this one done in this video, but we should get really far along. Okay? So let's say we want to determine the specific volume of superheated water vapor given a pressure and a temperature. And we're going to do it 3 different ways. We're going to do compare and contrast. We're going to find this 3 different ways. And so start a new example problem. I've got, so the given information here, I have water. I have a pressure of 3.5 megapascals, and I have to assume that's absolute. Given a temperature here of 450 degrees C, and they want me to find or estimate the specific volume using ideal gas law. Now again, unless the problem tells me to, I'm not going to use ideal gas law for water or R134. Our superheated tables are much better than ideal gas law will be, but they're asking me to. They're saying part A, using the ideal gas law, or ideal gas equation, find the specific volume. Okay, well, to do that, I need the ideal gas law, and that's just simply PV is equal to RT, right? That's not too bad. Okay, well, I have P and I have T, and I'm looking for V, so I've only got one unknown, and I'm just going to have to go look that guy up. So somewhere on your paper, am I right? Properties. Okay, so given that it's water, it's really all I would need to know to go look up an R value. That's what I would suggest, is put tabs in your book where the metric unit tables start and the English unit tables start. I've not done that yet. I'm going to. So you guys don't have to sit here. I don't have to try to fill the space while I'm looking up values. So I've got here table A1, and down here at the bottom, I don't know if you can see that, I've got water, and I'm going to go look up the R value, the gas constant, the R value. I'm going to go look up the R value for water. You need to know how to do the same, so you probably want to have your book out and do the same thing. Now this is metric units, so make sure we pull the metric value. For water, the R value is 0.4615, and the units for an R value is going to be energy, it's kilojoules per mass, it's kilograms per temperature, kilojoules per kilogram Kelvin. Okay. Okay, so engineering problem-solving strategy says identify what you know. What are you looking for? What do you know? What are the fundamental expressions to find it? Do you have enough information to solve? If not, go look up whatever else you need or find another equation. Well, I've looked up what else I need, so now I'm ready to solve. So I can say, well, that specific volume is equal to, we solve for that, that's R times T divided by P, right? Okay. Found the R value. That's 0.4615 kilojoules per kilogram Kelvin. Temperature. What is my temperature? The common thing is, if I'm doing this in class, somebody will say, oh, it's 450. Yes, it is 450. So what is my temperature? To go into ideal gas law, I cannot use that Celsius value. Right? That will blow this thing up, because Celsius values can have negative values. That will blow this thing up. It doesn't work. I need, I think it's 723 Kelvin. I has the dumbs tonight. So, I don't think yep, 723, all right. 723, like I say, I have, for some reason I has the dumbs. I literally started a video a second ago and I just said, nope, nope, we're just going to so I restarted a video where like about a minute and a half into it, I was like, no, I don't like any of those. So, okay, RT divided by pressure, 3.5 megapascals. You know what, let's just leave it, 3.5 megapascals. We're not going to like that later, I can tell you that. We're not going to like that unit set later, but let's leave it for now, okay? Okay. Make sure I don't have a glare on this. Have a glare right there? I don't have a glare right there, okay. So, 0.4615 times 723 divided by 3.5. And I get this number. So numerically it is 95.33. And we need to look at the units. Wow, okay, that is kilojoules. I've got kilojoules per kilogram Kelvin multiplied by Kelvin. So the Kelvins go away. So I've got kilojoules per kilogram per megapascals. Now what the heck am I going to do with that? Well, the common thing that I see a lot of people do is say, oh, that's got to be meters cubed per kilogram, right? It's the metric system. It works out nice. Nope. It does work out nice if you're careful. We weren't careful here. So let's talk about what this is. So let's look at what this actually represents. Units. And as you guys are probably learning, if you're doing the homework right, you'll spend a lot of time trying to figure out your units. What the heck's wrong with that? So a megapascal, right? Now a pascal measures pressure. That's force per area. So a pascal is a Newton per meter squared. So this is kilojoules per kilogram over meganewton per meter squared. That's a megapascal. It'll be a meganewton per meter squared. This is a complex fraction, so we're going to flip it over. So this is kilojoules per kilogram times meter squared per meganewton. All right, well, maybe I can break a joule down, right? What is a joule? Well, a joule measures energy. Energy is force times distance. So you can memorize a joule as a Newton meter, or you can remember, well, this is force times distance because it's energy, so that's a kilonewton meter is a kilojoule per kilogram times meter squared per meganewton. Okay, now I'm getting somewhere. Notice the newtons go away, but I do have a kilo over a mega. So I'm going to have a factor of 1,000 there to deal with. Okay? But notice that if the newtons do go away, I've got meters cubed per kilogram if I deal with the kilo and mega there. Okay? So what you might do, there's a number of ways you can do this. I might suggest to you the simplest way to do this is, let's say that V is equal to, instead of this, right, let's say 4615 kilojoules per kilogram Kelvin, multiply by that 723 Kelvin, and then rather than dividing it by the megapascals, let's divide it by 3,500 kilopascals. Right? So notice that this is kilopascals, this is kilonewtons per meter squared, this is kilonewtons, meter squared over kilonewtons, and then this simplifies. This just simplifies to meters cubed per kilogram. So this will simplify to meters cubed per kilogram. I got to move the decimal place 3 places because I've divided by 1,000 now. So this is 0.09533, and the units there are meters cubed per kilogram. And I got to stop there.